Okay, so today we're starting into what is our first real physics unit. So the last couple of days we spent some time talking about a little bit of math and supporting stuff to kind of get us where we need to be. But our first real physics unit is vectors. Okay, well, we're going to talk about the types of values that we are going to see more often than not in the context of this class. Before we even get into vector quantities, we need to kind of take a half step back and talk about something called scalar quantities. Now, a scalar quantity, by definition, is simply something that can be completely described using two things: a number and a unit. All we need for a scalar quantity is a number and a unit. Now, the combination of that number and a unit is given a very specific name. It is called magnitude. And magnitude is something that we will talk about almost on a daily basis throughout this course. As you might find a little bit later in the year, we're looking for the magnitude of the force. That means I need a number and unit that would apply to force. Okay? What is the magnitude of the velocity? Okay, well, then we're going to be looking for a number and a unit pertaining to a velocity in that instance. Okay, so I just want you to become familiar with the term magnitude. So when you hear magnitude, we're solving for, well, we're solving for one thing, but what the expression is two: the number and the unit associated with it. Scalar quantities do follow the basic rules of algebra. You can take a scalar quantity, you can add them, you can subtract them. In certain instances, you can multiply them and divide them. And most of the numbers that you've thought about or worked with through most of your science courses and your math courses when they're doing real life problems have been scalar quantities. So this isn't necessarily a new idea, it's just giving it a name. Okay, so I want to talk about just a couple of quick examples, at least those that we have up here on the board, and then we'll come up with some on our own. Okay, the first example of a scalar quantity is a distance. Okay, and the example here given has 25 meters. Now, in this case, meters ends up being what we want as our preferred SI unit, but we can express distance in any number of units. That could be 25 feet, 25 miles, 25 kilometers. Okay? Right now, the unit piece is relevant, because if we're just saying, is it a scalar quantity, what do we need to have? The number and the unit. Now, when we ask for what is an example of a scalar, yes, the measurement of a distance is a scalar quantity, but if we were to say, Justin, I'd like to give an example of a scalar, the 25 meters, that is the scale. Okay? So we're talking about a number and a unit associated with that specific type of quantity. Okay? Same applies to speed. Okay? And of course, we have various ways of expressing speed. Okay? In this case, one on the board, 60 kilometers per hour, which is a lot of places outside of the U.S. and how they express speed. You go to Canada, you go to a lot of places in Europe or anywhere else around the world. A lot of people use kilometers per hour as their measurement for speed. But that could be 60 miles per hour, 60 feet per second. Now, they're all different actual values when we express them in different units, but just understand that the unit piece isn't necessarily what's important right now, at least in terms of identifying whether it is a scalar or not. Time, obviously, is a scalar quantity. If we go ahead and measure it, 15 seconds, 15 hours, 15 days, 15 years. Okay, and lastly, temperature, the 273 Kelvin, 0 degrees Celsius, 32 degrees Fahrenheit, are all the same temperature. I hope you understand that, just expressed on different scales. Okay, so I want to think for a minute before we kind of march on. I want for us as a class to generate some ideas. What are three different scalar quantities other than the four examples given here? And to push that a little bit further, I don't want an example of a distance, speed, time, or temperature. Think about what we've done before in any of your math or science classes. What would be an example of a scalar quantity? Volume. Okay. Now, again, volume itself. Okay, I'm okay with volume, but give me an example of a volume. That's very specific. 22.4 liters. Okay, but that is an example of something that would be a scalar quantity. We have the number, we have the unit, and so a volumetric measurement, absolutely. Carter, no? Okay, mass. Okay, 10 grams. Now, You'll see me kind of go on and on about this later. Let's change it to 10 kilograms, just because that is actually the proper SI unit. We'll explain later why your chemistry teachers lied to you. They do it out of convenience. Okay? But it's not wrong. Chemistry has the application, but the proper units for math should be so. Ryan, think you have another one?
16 gigabytes.
Okay. Okay, if we're trying to measure the storage capacity, okay, 16 gigabytes. Now, not necessarily in terms of physics, but in terms of computers and storage, that absolutely would be a scalar quantity. Do you have another one, Jeremy, you want to throw on the top? Okay, if we're talking about energy, 10 joules, okay, would be another way to do that, and that absolutely is a scalar quantity. So all good examples. We could probably go on and on coming up with more things. I know some of you are kind of fresh off the chemistry mindset, which is maybe that's why we got mass and energy and some other things, which is a good thing to think about. But physics, we want to kind of take things one step further than a scalar quantity. And this is what we spend our unit talking about, vectors. In a lot of instances, we need to be just a little bit more specific than using a scalar quantity in physics class. We look for vector quantities, which have three components to it. A vector has a number and a unit, which again is just our way of saying magnitude, but we also have to have a direction associated with it. And not everything in physics is a vector quantity, but it is the preferred way of us trying to collect our data. So a vector quantity, we could say, has magnitude and direction. I want to keep putting that out there because the term magnitude is something we really need to become comfortable with. But ultimately, we're looking for three things in a vector quantity. It needs to have a number, it needs to have a unit, and it needs to have a direction. If it doesn't have those three things, it is not a vector quantity. Vectors do not follow the simple rules of algebra. We will talk later, not today, but later within this unit, how we can go ahead and add vectors. It is possible to do that. But you can subtract them in certain instances, but you definitely are not going to be multiplying them and dividing them. They just simply don't have that capacity. Now, in the examples that we're going to give for vectors, especially for the first two, you will notice that even though we're trying to describe roughly the same thing, even the term that we use to describe them changes when they become vector quantities. It is no longer a distance. When it becomes a vector quantity, it's something we call a displacement. And so even though the numbers, again, are the same as the previous example, even though it's 25 meters, we have to have a directional component to it. So in this one, 25 meters east would be a good example of a displacement. When we talk about speed, speed in a given direction is no longer going to be called speed. When it becomes that vector quantity and we add the directional component to it, we talk about that as a velocity. So instead of the 60 kilometers per hour, we have to have a direction associated with it, 60 kilometers per hour north. Now, time and temperature do not have a vector equivalent. It's not like we can have time in a direction or have temperature in a direction. So understand these last two examples are two completely different examples, even though the displacement and the velocity are the vector components of what you need from our previous examples. Okay, acceleration, which we'll describe a little bit more later. And by acceleration being 2 meters per second squared, some of you should try to argue that that would not be a vector quantity based on what you see on the board. Why should you try to argue against that? Okay? You do not immediately see a direction with this. Okay? And I'm glad that we picked up on that piece of it. It still is a vector quantity. Why? Ryan, what do you think?
The direction is positive.
It absolutely is. Okay? When we go ahead and we start associating some of these quantities relative to a coordinate grid, simply the fact that it might be positive does indicate a direction. Now we would need a little bit more information. Let's say we knew this was acceleration along a horizontal axis or an x-axis. If that is a positive 2, well, that tells us the acceleration should be directed in a positive direction. And if you really think about this, how much in your daily lives do you really think about things in terms of north, south, east, west? Not very frequently, do you? But you are constantly thinking about directional pieces. How am I going to get from this class to the next one? You are thinking directionally. without necessarily associating it with a north, south, east, or west. So it's actually very infrequent that we end up using those designations. Okay? And the same with force. Okay? 100 newtons here. Okay? The fact that that is a positive value is telling us that whatever axis we're relating that to, it is going to be acting in a positive direction. So it does technically include that. Now, anytime you go near any airports, I'm sorry, question? Okay. Well, it actually would be very simple. How do we show it would be negative? Well, this would be a -2, okay, or it would be a -100. Okay. Now, we need more contextual information. Okay, see what the context of that is. Is that going to be, like I said, the acceleration along the x-axis? If it's negative, then where your reference is, it would be to your left. Does that make sense? Okay. Great question. Okay. Have any of you ever in life seen in one of these windsocks before? I bet you probably have at some point. Did you know that it is a very rudimentary way of measuring a vector quantity? Okay. The different colored rings on those windsocks are a rough guesstimate to figuring out the speed of the wind. Okay. So depending on how strong the wind is, the more colored rings that you would see horizontal. But more so than just that, doesn't it also point which the direction is traveling to? So it adds that directional component to that as well. So even though now we have digital anemometers that can go ahead and tell us exactly what the wind speed is at that moment, at that location, and also point in the correct direction, there is the analog version of that as well that's helping us to collect that information. Okay, what's the wind speed going to be, and what's the wind direction going to be? So not everything necessarily needs big fancy tools to find, but always good to know. All right, so now we kind of know a little bit about this. Again, just a review with vectors. We need to have number, unit, direction. How are you going to represent a vector graphically? And this is something that we'll need to do and need to do relatively well. A vector is going to be represented graphically by drawing an arrow. The length of that arrow is going to represent the magnitude. So let's say we have two vector quantities, and let's kind of use force as an example. Force is any push or pull on an object. If we have a force of 50 newtons and we have a force of 100 newtons, relatively speaking, the 100 Newton force arrow should be drawn twice as long as the 50 Newton force. And just related to each other, they should be, well, the longer it is, okay, the greater that magnitude is going to be. Okay, the shorter it is, the lower the value is going to be. Now, it is not something, I'm not going to ask you, okay, here are two vectors, I need you to draw one exactly half the length of the other if it's half the value, or some sort of prorated size. Don't worry about that piece of it. But just know, the longer the arrow is, the greater the value should be. And it is going to show the direction, by the direction the arrow points to. So, let me come up here. Let me go ahead and find my arrow tool. There we go. Okay, so let's draw green arrow, and let's start here and point that direction. Okay, so I've drawn this arrow up on the board. Okay. Relative to quadrants that I know you probably remember, what quadrant is this drawn in? First quadrant. I hope we know that we start in the upper right-hand corner and we go counterclockwise. We go 1, 2, 3, 4. And so we have something drawn here in the first quadrant. If it's a standalone vector just by itself, and we want to visualize it, okay, start it at the center of your coordinate grid. You're not always going to get a coordinate grid, but it's a good way to help us with certain things, as we will see soon. But here's a question I have for you. Just go ahead and put your eyes on the board. I want to take this exact vector as it is, and I want to slide that there. Have any of the properties of that vector changed? Has the length changed? No, so it's the exact same magnitude. Has the direction changed? No. Okay? So that is exactly the same vector. Okay? So in theory, we should be able to take this vector, slide it just about anywhere, and the vector itself stays exactly the same. Now, if I take this and we modify it in any other way, has that vector changed from the original? Absolutely. We changed the length of that arrow, so we've changed the magnitude. We've also changed the direction with it. The point being, we should be able to slide these anywhere. We don't need the coordinate grid in order to help us figure out the magnitude and direction of that vector. Okay? All right. Is it important in physics to have things notated properly? Absolutely. Okay? And I've kind of been lenient because of the math review stuff we've done so far this year, but now we're going to get into there's a very specific way in which it needs to be done. Okay? So vector notation, when it is handwritten, and a lot of times we can see these on problem sets, we're going to use the arrow notation, meaning, okay, we go ahead, we write, let's say, vector A, whatever that quantity is. Let's double up on this, okay? We got vector A. Above it, we are going to draw a happy little arrow to indicate it is a vector quantity. So anytime we're talking about vector A, we need to have a number, we need to have a unit, we need to have a direction. When just the magnitude is written, so we're taking the directional piece out of it, we just draw the letter without the arrow notation. Okay? The example we see here is wind velocity. So let's say we go back to our wind sock, okay, and we are measuring the wind velocity at that point. We would see that would be 30 miles per hour east. But if we were only then going to say, what is the magnitude of that velocity, we don't really care about the directional component to it, so then the notation would also change. Even though it's still basically a velocity value, v, without the arrow notation, 30 miles per hour. Now, vectors themselves, assuming they are the same type of vectors, they can be added two different ways. I'll show you the first way today, and the second way is going to take us a little bit of time to kind of develop an understanding. And we can do it graphically. We're going to do that in a little bit. And eventually we're going to build towards our understanding of how we can do this mathematically. Because, of course, in physics, we want to make sure that we can support the concepts of what's going on with the math. Okay. So on the board, okay, you see a couple of different examples where I have three completely different sets of vectors. Okay. First example here on the left, okay, we have a blue vector and we have a green vector. How do we add vectors graphically? We use what we call a tip-to-tail addition, meaning the tip of the first arrow is where the tail of the second one would begin. When we are adding vectors graphically, the process of adding them, it is all going to be tip to tail. We're not going to see two tips pointing together when we're adding the individual vectors. We're not going to see two tails together. Okay, so think of it this way. Okay? What if I gave Jack a set of directions that I wanted you to travel, some displacements to travel? Okay, let's just say we have, what, 1, 2, 3, 4, 5, 6. If I asked you to stand up, walk 6 meters to the east, and then, so that's one vector, 6 meters to the east, represented here by our blue arrow, then 1, 2, 3, 4, 5 meters north. Those are two separate vectors, but graphically we could represent them with that tip-to-tail addition. I think it's easy to think about it in terms of a displacement because you can think, oh, that's kind of like steps to get from point A to point B. Okay. Maybe it was a different set of directions. We asked Jack to walk south and then to walk northwest, okay, or to go northeast and then do west. Okay, but these are three just different examples of vectors being added tip to tail. Now these are only two vectors. Could we have three vectors? Could I have given Jack 3 different directions to travel? Or 3 different displacements to travel? Absolutely. Could I have given Jack 10 displacements to travel? If I gave it to you on a list, then it would be pretty easy to follow. I mean, we could do that. If we gave 100, we could do it. As long as they are like quantities, okay, we can add them all tip to tail. So that's nice and all. But really, what do we want to be able to do? At the end of the addition process, just like you would do in a math problem, we are going to find the resultant. If we were to ask you in math class, what is 2 plus 5, you would be finding the result of that. What is the result of 2 plus 5 in your math class? 7. That's That's the result. Okay? We are finding the resultant vector that we get from when we add these quantities together. Now, I have to say this is the textbook definition of how we go ahead and find the resultant vector. Once we have drawn it, I have an easier way to summarize it. It's always drawn from where you start to where you finish on your diagram. Wherever your starting point is where the start of your resultant would go, and then where you finish is where your resultant would end up. So let me get my handy little arrow tool again, and let's take a look at, make this one a little bit bigger, our first diagram. Where do we start in this first diagram? What do we call this happy little point here? The origin, okay? What quadrant did we finish in with our green arrow? We're 1. So we're going to have a resultant that would be drawn. Oh, come on, I want that to be red. Okay? So that would be our resultant vector. Now, do you see tips and tails coming together with the resultant? Yes. Okay, that's where there's a little bit of confusion that comes in. The individual vectors are all tip to tail, tip to tail. The resultant is always going to be from start to finish. Okay, so let me get my arrow tool again. This time let's make sure it's red. So we're going to start here again, the origin. What quadrant are we going to finish in our second diagram? The third. So our resultant would be drawn from there to there. Okay, and our third diagram here, our resultant will be drawn from where we start to where we finish. So in all of these instances, if we were to say, all right, Jack got lost on the directions, he knows he's at the finishing point, but doesn't know where everybody else is, and say, Cole, go ahead, I want you to follow the resultant. And we can describe that one also as a vector with a magnitude and a direction. That's where we would need to go. So, when we add vectors, tip to tail. When we find the resultant, it's always from start to finish. How would we state this mathematically? The resultant, vector R, is equal to vector A plus vector B. Now, if we given 3 sets of directions, then it would have been the resultant vector is equal to vector A plus vector B plus vector C. If we've given Jack 100 directions, well, we'd have a lot of work to do, but we could still do it. It's all possible. It could end up in the same place. That's perfectly fine. Then your resultant would be 0 units, and there's not really a directional piece to it because that we finish right back where we started. Okay? But it is entirely possible to have that. So we can send Jack on that 100 direction chase, and he's going to find out potentially he finishes right back where he started. All right. So adding vectors mathematically. In order to add vectors, we have to use the x and y components of those vectors. Okay? The x and y components are the horizontal and vertical sides of the right triangle made by that vector. So when we draw a vector, especially if it is 2-dimensional, we can turn that into a right triangle where that vector becomes the hypotenuse. And we simply draw in order an x-axis and a y-axis, and then we can go ahead and figure some things out based off of that. So we're going to see that trig that we've been working on the last couple of classes again. And just a nice simple statement, if the vector is parallel to either the x or y axis, one of those components is going to be 0. So if you have, let's just say we go back to the displacement directions we were giving Jack earlier. We just asked Jack to walk 5 meters to the east. Well, he's going to have an x component to that because he traveled along what we will say is our x-axis. But he has not traveled at all along our y-axis, so the y component would be 0. Well, if we sent him north, then the x component would be 0. Well, it would only not be a right triangle if we're traveling parallel to either axis, the x or y axis. If it is something that is 2-dimensional, meaning it's going to move in both the x and y axis on a coordinate grid, it's going to have those 2 components. And so the main focus of today, now that we've kind of gotten to a little bit of the mathematical piece of this, is we want to be able to leave here today being able to correctly calculate vector components. Okay. So let's go to sample problem A. And I do ask, I know that some of the stuff that we're going to talk about, once you kind of catch on, we may be able to move forward. Just kind of hang tight and work with me. Okay? So, sample problem A, what are the components of a vector that has a magnitude of 1.5 meters that is 50 degrees above the positive x-axis? The first thing we're going to do is we're going to learn how to properly draw these, and we will start with a coordinate grid. We are not always going to get a coordinate grid, but for right now, we will. So Mark, we take a look at what we have, 1.5 meters, 50 degrees above the positive x-axis. What quadrant is this going to be in? It's above, that should be an indication, the positive x-axis. Correct, it will be in the first quadrant. Okay. So here, where's the positive x-axis? We start our origin, we go to the right, and then it's going to be above that. So this is our first quadrant. Now, do these have to be perfect? No. This is a visual representation of what's going on. 50 degrees is going to be slightly greater than 45 degrees. So I don't know. For me, that's how I will go ahead and draw. How do we then draw this into a right triangle? I have to say the order of this is very, very important. We must go x-axis first. So, if you were to try to describe this arrow, and you could only use left or right, because that would be along the x-axis, would you say it would go to the left or to the right? It would go to the right. So we're going to start here at the origin, and we're going to draw in the x component going to the right. And then from there, if we can only describe it as an up or down on this coordinate grid, how would we go to finish that right triangle? It would go up. Okay, so that is our right triangle. So now a couple things about notation. Because this is sample A, we're going to label our hypotenuse as vector A. The x component of this, we will label as A with x as a subscript. And if that be the case, what are we going to label our y component? AY. Now, why do we have to draw the x component first? Because 99.9% of the time, we are going to have our reference angle be with respect to the x-axis. And if we draw the y component first, that would take us up and then over. Is that going to include our reference angle? No. So we have to do the x-axis first. Really, there's only going to be two exceptions to that rule. And one of them comes in December, the other one comes in May. Okay? So everything else, okay? Most of those angles are going to be with respect to the positive x-axis. Or if we're told, the negative x-axis. So that would be in either our second or third quadrant. Okay. So now let's talk about the setup in terms of the calculation. So we want to find the x component. I want to find the value of AY. Do we know any of the values? Obviously we know the angle, but do we know any of the sides of this right triangle? We know the hypotenuse on this right triangle, the vector itself, and it has a magnitude of what? 1.5 meters. So we know that as a quantity. We have the hypotenuse. AX in this right triangle, is that the adjacent side or the opposite side? The adjacent. So what trig function would we use that incorporates the hypotenuse and the adjacent side? Cosine. Okay? So I want to talk our way through this the first go around. So good. We'll use the cosine function. So without writing this down yet, let's talk our way through this. Cosine of theta would be equal to the adjacent over the hypotenuse. But we want to get the adjacent by itself. So what would we do? The cosine of theta times the hypotenuse, correct? So AY will equal our hypotenuse, which is labeled here as what? Vector A, times the cosine of theta. That is a rearranged version of that, right? Question? This is, oh, I'm sorry, AX. Thank you. Okay, so we have AX equals A cosine theta. This is the rearranged equation for what we need, step one. Now it should be pretty easy. Do we know the value for vector A? What's the value? 1.5. We do not, at this point, please do not put your substitution in with units. Okay? The units do not go in the substitution. I know chemistry probably drilled that into you. We're not going to do that in the context of physics. 1.5 times the cosine of what angle? Okay? 50. I know we said it earlier, but we are going to make sure that we are in degree mode. I would like for everyone right now with your calculators to go ahead and find that value. Okay, so 1.5 times the cosine of 50. And do make sure that as we do that, we are going to express that out to the thousandth place if necessary. 1.5 times cosine of 50. And Sarah, when you believe you got a quality response, let us know. 0.964. Good. What would the unit be? It is going to be expressed in meters. Now, there is something we need to check. Is that going to be a positive component or a negative component? It would be positive. Okay? We would just leave that as such. Okay? You don't have to put a plus in front of that just to prove that it is a positive value. But the fact that it is not a negative is significant. Imagine for a moment that we did the exact same right triangle, but we did it in the second quadrant, starting at the origin going that direction. We would still calculate 0.964 because using the same numbers, we get the same value. But we then have to make an assessment. Look at what our diagram says. If it's going to the right is in a positive direction, so it should be a check for us. If we were going to the left, no matter what we would calculate, it should be what kind of value? Negative. In the same way, once we calculate it, we'll check along our y-axis. Okay? Now, Justin, I appreciate you picking up on this earlier. Now we'll do AY. Question? No. Because you cannot uniformly describe your hypotenuse in a direction at this point. At least simply not in terms of positive or negative. Now, if this was exactly 45 degrees, then I would say yes, you could. But for right now, no.
If you have a triangle and you have 4 and you compare it to y, would it be negative or positive?
It's a great question. Can I get through both these and I'll come back and revisit? Okay? Awesome question. Okay? So now we go to solve for AY. Obviously not the adjacent side anymore. Now what do we have? This is the opposite side. Okay? We'll still leave it as y, but now we have the opposite side and the hypotenuse is still a known quantity. So what trig function are we going to use for that? Sine. Okay? And in the same way, we would do the same rearranging. It would be our hypotenuse in vector A multiplied by the sine of theta. Well, this becomes a pretty simple substitution as well. But now, with the sine function, we can go ahead and recalculate what AY should be. Isabella, got a good answer? Units? Okay, 1.149 meters. Let's do our check here. Should that be a positive y component? Yes. Now, Julie, your question about, kind of seeing in different quadrants. Obviously, in different quadrants, we would maybe have a little bit different result, but it's no different than coordinates in there. Because if we're in, you remember from math class, quadrant 1, both x and y components have to be positive to put you into that quadrant. Okay? Same with quadrant 2. Your x would have to be negative. Your y would have to be positive. Quadrant 3, both negative. Okay? Then for quadrant 4, it would be a positive x, negative y. And it is always a worthwhile check. Once we get here at both components, check whether they're going to be positive or negative. And I guess here's what I would do. I know this one does not have north, south, east, or west, which I actually like. How would you describe the direction of your hypotenuse? You would probably say this would go to the right and up. So the right piece would, well, that's along our x-axis, that's a check for us. And it would be up, so that would be a check for our y-axis. Okay, so that way, whatever, or if you prefer just the quadrants, because you remember that from math, hey, quadrant 1 is this, 2 is that, 3 is that. Even though, at some point soon, we're going to take this coordinate grid away, you can still say, if it's above the positive x, I know it's going to be to the right and up.
Yeah.
So that we don't necessarily need the coordinate grid to figure that out.
Okay. So when you're like trying to think about the sign of the like A, Y, you look if it's like up and down, along the axis.
Look along that axis.
Okay.
Because that's what the component is.
Okay.
It is the magnitude of whatever this hypotenuse is along the x-axis and then along the y-axis. Okay? And here's the nice thing. If we do it right in drawing it, and we're always using this as our reference angle, the trig function should always remain the same. Because if we're over here, let's say in quadrant 2, okay, with an included angle, okay, then that's still going to be the adjacent side. The x is always going to be the adjacent. The y is always going to be the opposite. Okay, so here's what I would like for you to do. We're going to do 3 more samples together. Well, I'll have you do 3 samples, but I want you to read in a minute sample B, but we need to change the notation because we need to get used to seeing some different letters. Sample problem B, we will treat our hypotenuse as vector B. So what we'll be solving for would be bx and by. Then for sample C, okay, we'll go ahead and we'll do vector C with cx and cy. And then our 4th sample problem will be dx and dy. So I want us to go ahead and take, let's say probably about 5 to 10 minutes, and I want you on your own to go ahead and find what those components are going to be for those vectors. And we'll put them up on the board in a little bit. Okay, so let's come back and let's take a look at B. Okay, who is B? Oh, sorry. Oh, listen. So we go ahead and we take a look at what we have on the board. One, let's check our diagram. Okay, bx, by, and the hypotenuse. In this case, her diagram is expressed in the 4th quadrant. Is that where it should be? Absolutely. Do we agree with the diagram, where everything's placed, the labels? Okay. I think it's a very well done diagram. Okay. Then as we go ahead, we find b cosine theta, b sine theta. Be 12.042 kilometers and negative 8.432 kilometers. By show of hands, how many of you would agree with that as a response? Okay, you should. Okay. Now, okay, as I've kind of been having this conversation with a couple of you, take a look at how we've been doing all of these diagrams. If the x component is always drawn first, at least the things that we're dealing with right now, isn't the x component always going to be cosine? Because it's always going to be the adjacent side of whatever we have if we draw that x component first. Okay? Then, isn't the y component always going to be sine? For these examples, yes. Now, I need to put on my teacher hat for a second and say, there are going to be some examples later where that's not the case. So we can't just say x in every instance is going to be cosine and y in every instance is going to be sine. So can we agree to that right now? That's not always going to be the case. Yes. However, for 99% of the examples we're going to see, that is going to be the case. I just want us to know that is what we're dealing with. So, Alyssa, job well done on sample problem B. Okay. Sample C, Zion. Okay. Take a look at what we have here. We have airplane flying in a vector that is expressed above a negative x-axis. Okay? So should that land us in quadrant 2? Absolutely. We all agree with the diagram we see on the board? I would agree with what we have here. Okay, let's just go ahead and check our calculations. Okay, 55.716 meters per second, 33.477 meters per second. Listen to this question carefully. Do you agree with the values for those responses? The value, yes. The direction. Okay, what do we need to do? And this is the evaluation phase. Once we get the calculated value, we have to look at our diagram and ask yourself the question, what direction in this case along the x-axis do we need to go? To the left. So what should CX be? Negative 55.716. Okay? Then for CY, does it go up? Yes, so it should remain as a positive value for that. We have to go through that evaluation stage at the end. It's not just, can I get a correct value punching it into the calculator? We will always have to make that evaluation. Should it be a positive? Should it be a negative? And another check, and I probably should have said this earlier, but it's okay. We are calculating the two legs of the sides of the right triangle. Shouldn't they always be smaller than the hypotenuse? Yes, that's always a good check for us. Because sometimes we get so deep into a problem, we forget about some good process standpoints for our checkpoint. Okay? So if we were to get an answer for this that was like 108 meters per second for one component, we should know right off the bat that's not going to be correct. And we should maybe go back and check our work. I'm just saying that. Obviously, Ziad did fine with the calculation. And we want to make sure that occasionally we'll mistype something in the calculator. We're still processing what we're doing in addition to the calculations. Okay? And then Alexis, we have D. Okay? Are we in the correct quadrant for D as for what's up on the board? Yes. Okay? Third quadrant, so we know that both values should be negative. Both the x and y should be negative. Okay? And I have to say, job well done. Southwest, even though I kind of gave you a little bit of a precursor earlier, is a very exact direction. It is halfway between south and west. So we know what the angle should be with respect to the x-axis. What should it be? So 45 degrees. Okay? Now, technically, if it was, let's say, maybe a shallower angle, we could not say that that is southwest. Technically, it would be south of west. So we would go west, and then we measure south from that point. Okay? Or we could have north of east. That isn't necessarily northeast, but if we were 20 degrees north of east, well, then that would be, we have to go east first and then measure 20 degrees north from that point. Does that verbiage make sense? Okay. Good. But this one was exactly southwest, so that made that pretty easy to do. Okay, any questions on calculating vector components? Think you can do more? Good. Okay. That's what our practice is going to be for next class.